Alright, part 2 of related rates. I introduced related rates last time, and then we went through one example at a very slow pace, so I could sort of point out the things that we needed to do. Let's go ahead and deal with another problem on that same worksheet. And actually, if you put in related rates worksheet, this is a great worksheet. I used it last 2 years. It's online, and it actually has the answer key down at the bottom, so if you want to use it for practice, the ones that we actually don't do, it's actually a really good worksheet. Now this one says, an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. Oh, I know that there's a given right there, okay? So that's part of my given. If the distance s between the airplane and the radar station, and that means not along the ground, but sort of the diagonal. If the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when s is equal to 10 kilometers, what is the horizontal speed of the plane? Well, this is another Pythagorean. Okay, and we have the plane. Yeah, I'm not an artist. Okay, zoom. All right, and we know that this is the ground, and we have sort of a radar station over here, and we'll make it look like a little, antenna. Oh, isn't that neat? Now we know that the plane is sort of is going this way, right? According to our figure, and it's approaching, flying toward the radar station. Now we know that this right here is 6 kilometers, okay? 6 kilometers. And of course we usually refer to that portion, since this is along the bottom, and this is usually refer to that one as y. So y is equal to 6 kilometers. You can call it whatever you want. Now that's our given information. Now, remember I said that the when was basically what cued you last time? Sometimes it says if, okay? If is your cue word this time. If tells you you're dealing with conditional information now. So if, keyword, we're dealing with conditional information now. If the distance s, and so we're going to call this s, which they call it z, but I didn't make the worksheet, between the airplane and the radar station is decreasing, and decreasing being a key word there, that means it's going to be negative, at a rate of 400 kilometers per hour. So ds dt, the rate at which s changes with respect to time, is negative 400 kilometers per hour. Okay? When s is equal to 10 kilometers, so s is equal to 10 kilometers. Okay? Now, I know that I have a third dimension right here, which we're going to call x. I know that I'm probably going to need a value of x, and I know that it's basically going to be a piece of implied conditional information. Now, if at a moment in time y is 6 and s is 10, x at that moment in time has to be 8. It is a 3, 4, 5 right triangle, but that piece of information is implied. Okay, it is not explicitly given. Now, what I'm being asked for is what is the horizontal speed of the plane? So your question is, what is dx dt? Okay, again, all we need to do is we need to set up the Pythagorean relationship. I know that it's going to be x squared plus 6 squared is equal to s squared. S's wind up looking like 5s when you write too fast, which is why I try not to use them for variables, but whatever. And when we differentiate with respect to t, I'm going to get 2x dx dt plus 0 is equal to 2s ds dt. Now, of course, the 2's cancel out. The 0 is a non-issue. and I need to solve for dx dt. Now I can go ahead and solve for dx dt before I plug numbers in. That really doesn't matter. And you get that equation right there, and then you can just go ahead and plug in 10 for s, 8 for x, and those, of course, that's nice to have it in that ratio because their units are going to cancel out. And then ds dt is negative 400 kilometers per hour. Now this winds up being 5/4. So 5/4 times 400, or negative 400 in this case, is going to give you negative 500 kilometers per hour. That is your answer. Okay? All right. Let's go ahead and move on to one that is not dealing with a right triangle and Pythagorean. Let's go ahead and look at number 3 right here on this same worksheet. I'm just going to turn this piece of paper around. Okay. A conical cup is 4 centimeters across and 6 centimeters deep. Okay. Now, if you've ever, if you ever played sports or anything like that, you know that sometimes they have water jugs with a little thing of cups on the side, and you just pull the cup out, and it's almost like a snow cone sort of cup. It's a cone, right? And that's what it's talking about. A conical cup is 4 centimeters across and 6 centimeters deep. Okay. So let's go ahead and draw that. Remember, our first thing that we need to do is draw the scenario. Okay. And it's probably a good idea to go ahead, since you're talking about the measurement that is across. And of course, you're going to be talking about the measurement up and down. So we know that this right here is 4 centimeters. That measurement right there is 6 centimeters. Okay. It says water leaks out of the bottom at a rate of 2 cubic centimeters per second. Now, that is a piece of given information. Now, it's a weird piece of given information compared to the ones that we've already seen, because it is a constant, but we obviously can't plug it in until after we differentiate, right? Because this is dV dt. The water leaks out. The volume decreases at a rate of 2 centimeters cubed per second. Okay? Make sure it's negative, because if water's leaking out, the volume is getting smaller, and therefore dV dt has to be negative. Okay? Now, it's asking, okay, and you can put these in any order you want, how fast is the water level dropping? Okay, well, let's call the height of the water h. So dH dt is what when the conditional information is, okay, well, when the height of the water is equal to 3. Okay? So that's the full cup right there, but you know that, the water is not always filled up all the way to the top, right? Okay, well, so here's the thing. It's probably a good idea to go ahead and put, another thing across here. And then all of a sudden, or at least I should, I see something in there. I see a triangle right here. Okay, and that doesn't show up on the camera very well. Let me go ahead and use an old school highlighter. Okay. I see a triangle right there. You want to know what else I see? I see a triangle right there. Now, what is the relationship between those triangles? Well, the answer is they're similar triangles, okay? So this triangle right here, this smaller one, is similar to this one. I know that because they're both right triangles, and they share this angle down here, okay? Geometry hasn't been that long ago, right? So if I have two angles that are identical, being the right angle and the shared angle, then the third angle has to be the same as well. So equiangular triangles are similar triangles. Well, that's kind of nice. Well, let's go ahead and label our variables. I know that this right here is going to be h, okay? This right here, since we're dealing with a cone, is r. Now, there are two things that I need. I happen to know that the volume of a cone is pi over 3 r squared h. But I don't want to deal with that, okay? I don't want to deal with that. Largely because if I do, I'm going to have three variables, okay? But I happen to know that if I'm dealing with similar triangles, if the top diameter is 4, then the radius is 2. And therefore, I know that 2 to 6 is equal to r to h. Does that make sense? Okay? And therefore, h is equal to 3r, or r is equal to 1/3 h. Okay? H is 3 times r. Now, that's really kind of neat, because if h is r times 3, then I have a piece of implied conditional information right here. When h is equal to 3, r is equal to 1. Implied conditional, right there. But not only can I use this similarity between the sides to get an implied conditional, I can actually use it to plug in to here and arrive at an equation in terms of a single variable. The question is, which one do I use? Well, I don't want to get rid of h if I'm solving for h. Okay, so I want to get rid of r. So if r is equal to 1/3 h, or it's probably better to think about it in terms of h over 3, then r squared is h squared over 9, and v becomes pi over 27 r cubed. Okay, now that was only true for this particular scenario. So don't just plop down pi over 27 r cubed every time you wind up having a cone, because a cone will be of different dimensions, and you'll have to substitute accordingly. Now, this is a constant. So really, when I'm differentiating, I'm just differentiating r cubed. So dv dt is equal to pi over 9, once I bring the 3 down and combine it with this, r squared, or sorry, that's supposed to be h, h squared, dh dt. Well, that's kind of neat, okay, because I know h, okay, and I know dv dt. So if I know dv dt is -2 centimeters cubed per second, and that becomes pi over 9 times 9, because h is 3, so h squared is 9, times dh dt. And guess what? Those 9's cancel, and all I have to do in order to figure out dh dt is to divide by this pi right here. Okay. Now, of course, I haven't put the units over here on the right hand side. That's supposed to be centimeters squared, right? So this winds up being -2 over pi centimeters per second. Okay. Now, that I've done 2 more for you. I've done one which involved right triangles. I've done another one which involved similar triangles embedded within a cone. But it was the same sort of procedure that I went through every single time. Draw the picture. Identify the given information, the question, and the conditional information, trying to figure out any implied conditional information that might be necessary. Determine the equation which is going to be governing this scenario. Make any substitutions necessary. Differentiate with respect to time. Plug in, solve. Okay, yeah, easier said than done, I know. But that's the basic sort of flow that we're going to go through in all the rest of the examples that I'm going to do. That brings us to a little more than 15 minutes on this particular one. Video 3 will start up, and I will move on to probably one involving a sphere, and we'll sort of have fun with that.